In 1998, astronomers studying distant supernova explosions discovered something that should not exist according to every prediction of modern physics. The universe, which should have been slowing down from the pull of gravity after 13.8 billion years of expansion, was instead accelerating, speeding up, moving faster with each passing moment toward some unknown fate. Deep within the mathematical equations describing reality, buried in observations that challenge our most fundamental assumptions, lies evidence of phenomena so bizarre that 95% of the universe must be made of substances we cannot see, cannot touch, and barely understand. What if everything we think we know about the cosmos is wrong? What if dark energy is not a constant force, but something that changes, evolves, and may already be weakening? What if the universe is not expanding forever, but heading toward a catastrophic big crunch that will collapse all of space-time? Today, we journey through 101 weird facts about the universe that reveal why reality may be stranger than we can possibly imagine. Prepare yourselves. We begin. The universe is 13.8 billion years old, but this number represents only the time since the Big Bang, the age of the observable universe. What came before the Big Bang, if anything, remains one of physics' deepest mysteries. The concept of before may not even have meaning, as time itself appears to have been created in the Big Bang along with space, matter, and energy. The observable universe extends approximately 46.5 billion light-years in every direction from Earth, despite being only 13.8 billion years old. This apparent paradox arises because space itself has been expanding during the time light has been traveling toward us. Objects that were relatively close when they emitted the light we see today have since moved to distances far exceeding what light could have traversed in the age of the universe. The universe has no edge or outside. Every point in space can equally claim to be the center of the universe, and the cosmos extends in all directions from any location you choose. This counterintuitive fact emerges from the fundamental geometry of space-time, which appears to be either infinite or closed back upon itself like the surface of a sphere. Dark energy comprises approximately 68% to 70% of the total mass energy content of the universe. This mysterious force pushing space apart and accelerating cosmic expansion represents the largest component of reality by far. Yet we have never directly detected dark energy and understand almost nothing about its fundamental nature. Dark matter constitutes another 27% of the universe, leaving ordinary matter, everything we can see, touch, and measure, as a mere 5% of cosmic content. The atoms making up stars, planets, and our own bodies are minority constituents in a universe dominated by invisible, poorly understood substances. The term dark energy was coined by University of Chicago astrophysicist Michael Turner in 1998, specifically to emphasize the profound mystery. Turner wanted a name that would prevent scientists from jumping to premature conclusions about what was causing the accelerating expansion. The name worked. Nearly 3 decades later, dark energy remains one of physics' greatest unsolved problems. Dark energy was discovered in the late 1990s through observations of type Ia supernovae in distant galaxies. Astronomers expected these explosions to reveal a universe gradually slowing down from gravitational attraction. Instead, the supernovae appeared dimmer than predicted, indicating they were farther away than expected, if expansion had been constant or decelerating. The observations won the 2011 Nobel Prize in Physics. Recent evidence from the Dark Energy Spectroscopic Instrument, DSI, suggests that dark energy may not be constant but instead evolving over time. Data from 6.4 million galaxies and quasars indicate that the relationship between dark energy's density and pressure has changed throughout cosmic history. If confirmed, this finding would rewrite our understanding of the universe's past and future. DESI's results hint that the equation of state parameter W for dark energy was lower than 1.4 in the distant past. slowly increasing to approximately 0.8 today. Traditional cosmological constant models require W to equal exactly 1.0 and remain constant. The deviation suggests dark energy is not a simple property of space, but something more complex and dynamic. Multiple independent measurements all point toward changing dark energy. When DESI's baryon acoustic oscillation data are combined with observations of type Ia supernovae and cosmic microwave background radiation, the results consistently indicate variation over time. The convergence of evidence from different techniques strengthens the case that something fundamentally new is occurring. Some data now suggest the universe may have entered a phase of decelerating expansion. Research published in November 2025 indicates that cosmic expansion might no longer be accelerating, but has begun slowing down. If confirmed, this would represent a major paradigm shift, reversing decades of accepted cosmology since dark energy's discovery. The possibility of deceleration raises the specter of a big crunch, where expansion eventually reverses entirely and the universe collapses back toward infinite density. This catastrophic ending would occur billions or trillions of years in the future, but it represents one of several possible ultimate fates for the cosmos. Early dark energy may have existed during the universe's first 300,000 years before disappearing entirely. This hypothetical primordial form of dark energy could explain two major cosmological puzzles: the Hubble tension and the unexpectedly large number of bright galaxies observed in the early universe by the James Webb Space Telescope. The Hubble tension refers to a persistent 9% discrepancy between different measurements of the universe's expansion rate. When astronomers calculate the Hubble constant from cosmic microwave background observations, they get approximately 67 kilometers per second per megaparsec. When they measure it using nearby supernovae and other local phenomena, they get about 73, a significant mismatch that has persisted despite improved measurements. If early dark energy briefly accelerated expansion during the universe's infancy, it would increase the Hubble constant derived from early universe observations to match local measurements. The proposal represents one of the most promising solutions to the Hubble tension, though confirmation requires detecting subtle signatures and precise measurements of the cosmic microwave background. Early dark energy would also have affected how quickly matter clumped together in the early universe, potentially explaining why JWST has discovered so many large, bright galaxies existing surprisingly early in cosmic history. Standard models predict the early universe should have been much less populated, but observations consistently reveal mature galaxies when the cosmos was less than 1 billion years old. The cosmological constant problem represents perhaps the worst prediction in the history of physics. When quantum field theory calculates the vacuum energy density that should exist in empty space, the result exceeds observations by a factor of 10^120, a 1 followed by 120 zeros. No other physics prediction has ever been this spectacularly wrong. Quintessence offers an alternative to the cosmological constant as an explanation for dark energy. Rather than a fixed property of space, quintessence proposes a dynamical scalar field that varies in both time and space. The field would behave opposite to normal matter and energy, driving cosmic acceleration while potentially changing strength over cosmic history. Some theories suggest dark energy and dark matter might be different manifestations of the same underlying phenomenon. Though currently treated as completely separate substances, both represent unknown forms of energy matter that interact primarily through gravity. A unified explanation could revolutionize our understanding of cosmology. Dark energy is often described as having negative pressure that pushes space outward. However, this description involves significant simplification. We don't actually know if dark energy exerts any type of force at all. The negative pressure description emerges from how dark energy must behave in Einstein's equations to produce accelerating expansion. The Vera C. Rubin Observatory began scientific operations in 2025 with the world's most powerful digital camera. Located in the Chilean Andes, Rubin is discovering more than 20,000 new supernova host galaxies. providing unprecedented data about cosmic expansion across different epochs. These observations will either confirm or refute the varying dark energy hypothesis within the next few years. NASA's Nancy Grace Roman Space Telescope, launching soon, will conduct extensive surveys specifically designed to probe dark energy's nature. Roman's field of view is 100 times larger than Hubble's, while maintaining similar resolution, allowing it to map matter distribution and dark energy behavior across vast cosmic volumes. The ESA's Euclid mission, launched in 2023, is creating the largest 3D map of the universe ever attempted. Euclid's observations of billions of galaxies over the past 10 billion years will reveal how dark energy has influenced cosmic structure formation throughout the universe's history. Together, DESI, Roman, Rubin, and Euclid are ushering in a golden age of dark energy research. The combined observations from these projects will either confirm the standard cosmological constant model or reveal new physics that requires fundamental revisions to our understanding of reality. Baryon acoustic oscillations, BAO, provide a standard ruler for measuring cosmic expansion across different epochs. These characteristic ripples in galaxy distribution originated from sound waves in the primordial plasma before the universe became transparent. As space expanded, these ripples grew proportionally, creating a feature at approximately 490 million light-years that serves as a cosmic measuring stick. The cosmic microwave background radiation is the oldest light in the universe, released 380,000 years after the Big Bang, when the cosmos finally cooled enough to become transparent. This relic radiation fills all of space and maintains a nearly perfect temperature of 2.725 Kelvin, just above absolute zero. Tiny temperature fluctuations in the cosmic microwave background, variations of mere millionths of a degree, reveal the seeds that grew into all cosmic structures. Slightly denser regions in the early universe appears slightly warmer spots in the CMB, while less dense regions appear cooler. These quantum fluctuations, stretched to cosmic scales during inflation, determined where galaxies, clusters, and vast cosmic voids would form. The universe underwent a brief period of exponential inflation during its first fraction of a second. In roughly 10^36 seconds, space expanded by a factor exceeding 10^26, growing from subatomic scales to macroscopic size, faster than light could cross the original volume. Inflation explains why the universe appears so uniform and why it's geometrically flat. The cosmic neutrino background fills the universe with particles even more abundant than photons from the cosmic microwave background. These neutrinos, released just 1 second after the Big Bang when the universe cooled enough for them to decouple from other matter, carry information about even earlier cosmic epochs than the CMB reveals. Neutrinos are the most common particles with mass in the universe. 1 trillion neutrinos pass through each of your fingernails every second, traveling at nearly the speed of light without interacting. Despite their incredible abundance, neutrinos collectively contribute less than 1% of the universe's total mass energy. The universe is geometrically flat to within 0.4%, according to the most precise measurements. This means that parallel lines remain parallel across cosmic distances, rather than converging or diverging as they would in curved space. The flatness presents a puzzle, because any deviation from perfect flatness should have been amplified enormously during 13.8 billion years of expansion. The flatness problem is one of several fine-tuning issues, suggesting that the early universe required extraordinarily precise initial conditions. The density parameter, the ratio of actual density to critical density, must have been exactly 1.0 to within 1 part in 10^62 at the Planck time for the universe to remain flat today. The horizon problem asks why causally disconnected regions of the early universe had identical properties. Parts of the cosmos that could never have communicated because light hadn't had time to travel between them somehow possessed the same temperature, density, and physical characteristics. Cosmic inflation solves this by proposing that all observed regions originated from a single causally connected patch. The smoothness of the cosmic microwave background across the sky implies that regions separated by more than the horizon distance at the time of last scattering somehow coordinated their properties. Without inflation, this coordination would require faster-than-light communication, violating relativity. Inflation allows the coordination by making these regions share a common history before exponential expansion separated them. The universe contains roughly 2 trillion galaxies according to estimates combining observations from multiple surveys. This number far exceeds earlier estimates and continues growing as deeper observations reveal ever more distant galaxies, invisible to previous instruments. The Milky Way galaxy contains between 100 and 400 billion stars. The enormous range reflects the difficulty of counting stars hidden behind dust, faint red dwarfs, barely visible even with powerful telescopes, and the uncertain mass contribution from brown dwarfs and stellar remnants. Each galaxy likely contains, on average, as many planets as stars, meaning the observable universe hosts roughly 10 to 24 planets. This incomprehensibly large number suggests that even if planets suitable for life are extremely rare, the cosmos should contain vast numbers of potentially habitable worlds. The observable universe is estimated to contain approximately 10^80 atoms. This number, while staggering, represents a finite quantity that could theoretically be counted given sufficient time and perfect instrumentation. Most normal matter in the universe exists not in stars, planets, or galaxies, but in the filaments of hot, ionized gas comprising the cosmic web. These tendrils connecting galaxy clusters contain more ordinary matter than all visible structures combined, remaining largely invisible, except where they block light from background quasars or emit faint X-rays. The cosmic web is the largest known structure in the universe, with galaxy clusters residing at the nodes, where filaments intersect, and vast cosmic voids filling the spaces between strands. This foam-like structure extends across billions of light years and appears to be shaped primarily by dark matter's gravitational influence. The largest individual structure discovered is the Hercules Corona Borealis Great Wall, spanning approximately 10 billion light years. This immense filament of galaxy clusters challenges theoretical limits on how large structures can grow through gravitational collapse during the universe's finite age. The cosmic web structure is remarkably similar to neural networks in the human brain, with similar branching patterns and connectivity. This similarity is purely coincidental, arising from mathematical rules governing how networks self-organize, but highlights deep connections between complexity at vastly different scales. The universe is isotropic and homogeneous on large scales, meaning it looks statistically identical in all directions and from all locations, when averaged over distances exceeding several hundred million light-years. This uniformity represents one of cosmology's foundational principles and provides crucial evidence for the Big Bang model. The cosmic principle states that the universe has no special locations or preferred directions. Earth occupies no privileged position, and the same physical laws apply everywhere throughout space and time. This assumption underlies all modern cosmology and appears validated by observations showing consistent properties across vast distances. Quasars are the most luminous, persistent objects in the universe, powered by supermassive black holes, consuming matter at enormous rates. The brightest quasars shine with the light of trillions of stars from regions smaller than our solar system, making them visible across most of the observable universe. The most distant quasar ever observed existed just 670 million years after the Big Bang, when the universe was only 5% of its current age. This quasar's central black hole contains more than 1 billion solar masses, raising profound questions about how such massive black holes form so quickly. Redshift measures how much the universe has expanded since light began its journey toward us. A redshift of Z1 means the universe has doubled in size since the light was emitted, while Zeta 2 indicates the cosmos is 3 times larger than when the photons started traveling. The most distant objects show red shifts exceeding Z11. Gravitational lensing by massive galaxy clusters can magnify distant background galaxies by factors of 10 to 100, allowing astronomers to observe objects too faint and distant to see directly. These natural cosmic telescopes have revealed some of the earliest galaxies, providing windows into epochs otherwise inaccessible to current instruments. Strong gravitational lensing creates multiple images of background objects, sometimes forming complete Einstein rings when alignment is perfect. The distorted images encode information about the lens mass distribution, including dark matter, making gravitational lensing a powerful tool for studying the universe's invisible component. Weak gravitational lensing subtly distorts the shapes of background galaxies, creating patterns that reveal how dark matter is distributed across vast cosmic volumes. By analyzing millions of galaxy shapes statistically, astronomers can map dark matter's large-scale structure, despite it being invisible to telescopes. The Lyman alpha forest consists of numerous absorption lines in quasar spectra, caused by intervening hydrogen gas at different distances. Each absorption line represents a cloud of neutral hydrogen along the line of sight. And analyzing these features reveals how gas was distributed throughout cosmic history. The epoch of reionization occurred when the first stars and galaxies formed, emitting ultraviolet radiation that ionized neutral hydrogen, filling the universe. This transition from a neutral to an ionized cosmos took place between roughly 150 million and 1 billion years after the Big Bang, marking a fundamental shift in the universe's properties. The first stars, called population 3 stars, were likely hundreds of times more massive than the Sun and composed of pure hydrogen and helium with no heavier elements. These hypothetical objects have never been directly observed, but their existence is inferred from the chemical enrichment patterns seen in later stellar generations. Metallicity in astronomy refers to the abundance of elements heavier than helium. The first stars had zero metallicity, while subsequent generations incorporated metals forged in supernova explosions from earlier stars, progressively enriching the cosmos with carbon, oxygen, silicon, iron, and all other heavy elements. The universe was completely opaque during its first 380,000 years, filled with hot plasma, where photons constantly scattered off free electrons. Only when the cosmos cooled below 3,000 Kelvin could electrons combine with protons to form neutral atoms, allowing light to travel freely for the first time. The surface of last scattering refers to the spherical shell surrounding us, from which the cosmic microwave background originates. This shell represents the furthest distance we can observe using photons. Everything closer is transparent. Everything farther remains hidden behind the opaque early plasma. The oldest known rock formation on Earth is the Nouveau-Guitook outcrops in northern Quebec, dating to 416 billion years ago. These rocks formed during the Hadean Eon, preserving remnants of Earth's ancient ocean floor from the first 400 million years of planetary history. Earth's inner core recently reversed its spin direction and continues changing shape, with deformations in its shallowest levels revealed by seismic studies in February 2025. These discoveries demonstrate that our planet's deep interior remains dynamically active in ways we are only beginning to understand. Magnetic north has been drifting from Canada toward Russia since its discovery in 1831, with the movement accelerating dramatically in 1990, from 9.3 miles per year to 34.2 miles per year. The drift slowed around 2015, but continues, requiring regular updates to navigation systems worldwide. Gold from Earth's core has leaked to the surface according to May 2025 research on Hawaiian rock formations. This raises the fascinating prospect that more precious metals could continue migrating from the planet's center to the crust over geological timescales. The sun's nuclear fusion occurs only in its innermost quarter, a tiny sun within the sun, where temperatures and pressures are sufficient to fuse hydrogen into helium. The visible surface we observe merely marks where this energy finally escapes after spending roughly 100,000 years diffusing outward from the core. The Parker Solar Probe made history in 2024 by flying within 3.8 million miles of the solar surface, closer than any spacecraft had ever approached. The probe survived temperatures exceeding 2,500 degrees Fahrenheit while gathering unprecedented data about the sun's corona and the solar wind's origins. Betelgeuse, the red supergiant star in Orion, has a small companion star, a beetle buddy, that explains the bizarre glowing patterns puzzling astronomers for years. This companion, confirmed using speckle imaging in July 2025, causes Betelgeuse's brightness to vary on a 400-day cycle with a secondary period of roughly 6 years. Neptune's aurorae were finally observed in all their glory in March 2025 by JWST's infrared capabilities. Unlike Earth's polar aurorae, Neptunes occur over regions equivalent to where South America would be on our planet, due to the ice giant's magnetic field being tilted 47 degrees from its rotation axis. A new moon orbiting Uranus was discovered in August 2025, bringing the planet's total to 29 known satellites. The moon, provisionally designated S2025U1, is only about 9.6 kilometers in diameter, explaining why it remained invisible in previous observations, despite likely appearing in Voyager 2 and Hubble images. Venus is the slowest spinning planet in the solar system, rotating so gradually that a person could walk faster than its surface moves. A Venusian day lasts longer than a Venusian year, with the planet taking 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun. Jupiter's Great Red Spot is the largest storm in the known universe, a hurricane 3 times wider than Earth that has been raging for at least 350 years. The storm floats approximately 5 miles above Jupiter's cloud tops, though the planet technically has no solid surface beneath its thick atmosphere. Neptune has the strongest winds in the solar system, with atmospheric currents howling at 1,300 miles per hour, 4 times faster than Earth's fiercest tornadoes. The mechanism driving these extreme winds on a planet so far from the Sun remains poorly understood. Helium is the only element that never freezes solid under normal conditions. No matter how cold temperatures become, helium remains liquid unless subjected to extreme pressures, exceeding 25 atmospheres. This unique property arises from quantum mechanical effects that keep helium atoms in constant motion even at absolute zero. Half of the moon is composed of oxygen, the same element that makes up 2/3 of human body weight. While lunar oxygen is chemically bound in rocks and minerals rather than existing as breathable gas, future astronauts might extract it for life support and rocket fuel. After meteoroids or spacecraft strike the moon, it vibrates like a bell for hours. This prolonged ringing occurs because the moon's interior is cold and rigid, lacking the damping effects that would quickly quiet vibrations in warmer, more fluid planetary cores. The asteroid Bennu, sampled by NASA's OSIRIS-REx mission, contains all the ingredients for life as we know it. Analysis published in December 2025 revealed that Bennu's materials include water, organic compounds, and multiple sugars, with the notable exception of deoxyribose, the DNA sugar, supporting the hypothesis that RNA preceded DNA in life's origins. The missing deoxyribose sugar supports the RNA world hypothesis, which proposes that Earth's earliest life forms consisted of RNA molecules that both stored genetic information and catalyzed chemical reactions. DNA would have evolved later as a more stable information storage molecule. Leopard spots on a Martian rock discovered by the Perseverance rover in July 2024 represent the clearest potential biosignature ever found on the red planet. The distinctive patterns contain minerals and textures that on Earth are almost always associated with microbial metabolism, though non-biological explanations cannot yet be completely ruled out. The rock, nicknamed Chayava Falls, contains organic carbon, sulfur, oxidized iron, rust, and phosphorus, all ingredients necessary for life. The combination of these elements with the leopard spot patterns creates a compelling case that microorganisms may have once inhabited ancient Martian waterways. coherent elastic neutrino nucleus scattering, C-EVENS, was finally observed in July 2025 after 50 years of searching. First theorized in 1974, this effect involves neutrinos scattering coherently against entire atomic nuclei rather than individual particles, creating tiny nuclear recoils previously too small to detect. The universe could end in a big crunch if dark energy continues weakening, as some data suggest. In this scenario, cosmic expansion would eventually reverse, causing all matter to fall back together in a catastrophic collapse, mirroring the Big Bang in reverse. This dramatic ending could occur roughly 33 billion years from now, based on current deceleration rate estimates. The standard model of particle physics may require revision if dark energy is truly time-varying. This model, which has successfully described fundamental particles and forces for decades, assumes certain cosmological parameters remain constant. Variable dark energy would necessitate extending or replacing the standard model with new physics. The universe's temperature has been cooling steadily since the Big Bang, declining from infinite temperature at T0 to the current 2.7 Kelvin average. This cooling will continue as expansion proceeds, with the cosmos approaching absolute zero over trillions of years, as matter and radiation become ever more diffuse. The density of neutron stars equals what you would have after crushing a cruise ship until it's the size of a ballpoint pen ball. These incredible objects contain matter so compressed that atomic nuclei are packed together like grains of sand, creating material billions of times denser than anything on Earth. The fastest spinning pulsars rotate 716 times per second. From such a pulsar's surface, other stars would appear not as dots, but as white streaks in the sky due to the extreme rotation speed. The second fastest known pulsar spins 614 times per second. The extent of the known universe spans 38 to 47 billion light years in every direction, encompassing everything we can theoretically observe given light's finite speed and the cosmos' finite age. Beyond this horizon lies more universe we cannot see, because light from those regions hasn't had time to reach us yet. When observed from dark desert skies far from cities, the naked eye can detect approximately 2,600 stars, despite the impression of millions. You could count every visible star in about 20 minutes at a leisurely rate of 2 per second, though the vast majority of stars are too faint or distant to see without telescopes. The longest star name still commonly used is Zubin-esh Shamali in the constellation Libra. The shortest star name is simply the Sun. Both extremes demonstrate the evolution of astronomical naming from ancient Arabic traditions to modern simplicity. The Cosmic Horseshoe Galaxy harbors an ultramassive black hole, detected using a combination of gravitational lensing and observations from the Very Large Telescope and Hubble. This discovery, announced in 2025, demonstrates how lensing by massive galaxy clusters can reveal objects otherwise undetectable through conventional methods. El Capitan, the world's fastest supercomputer, was inaugurated in January 2025 at Lawrence Livermore National Laboratory in California, reaching exascale computing speeds with peak performance of 2.79 exaflops, 2.79 quintillion calculations per second. This $600 million machine will organize America's nuclear stockpile and design new weapons. 2024 was the first calendar year on record, with global average temperatures 1.6 degrees Celsius, 2.8 degrees Celsius, above pre-industrial levels. This stark milestone demonstrates the accelerating pace of climate change and highlights the narrow window remaining to prevent the most catastrophic effects. Dire wolves may have been resurrected by genetic engineering. In April 2025, Colossal Biosciences claimed to have created the first modern dire wolves, extinct for over 10,000 years, by editing 14 genes in gray wolf DNA to recreate key physical traits like larger size, bigger teeth, wider heads, and white fur. AI psychosis has emerged as a phenomenon where people mistake chatbots for conscious beings, driving them to hallucinate, have delusions, or confuse reality. Psychiatrist Keith Sakata reported seeing 12 patients hospitalized with this condition in 2025, mostly younger men, echoing concerns from the 1960s when people first confused Eliza, an early chatbot, for a real therapist. The universe operates on principles so strange that 95% of its content remains invisible to our instruments and barely understood by our theories. Every observation reveals new mysteries while partially solving old ones. Every measurement of cosmic expansion shows discrepancies, requiring either new physics or revolutionary reinterpretation of existing observations. We stand at an extraordinary moment in cosmic history, conscious beings capable of comprehending the universe's vastness while remaining fundamentally uncertain about its basic composition. We can measure space bending around massive objects, detect gravitational waves from colliding black holes, and peer back to when the first stars ignited. Yet we cannot explain the acceleration of expansion or identify what constitutes most of reality. The weird facts compiled here represent not final answers, but signposts pointing toward deeper mysteries. Dark energy may be changing. The universe might collapse. Expansion could be slowing right now. Alternative forms of dark energy might have existed in different cosmic epochs. The cosmological constant could be wrong. Within the next few years, the golden age of cosmology will deliver unprecedented observations. DESI will complete its massive galaxy survey. Roman will launch and begin mapping dark energy across cosmic history. Rubin will discover thousands of supernovae. Euclid will image billions of galaxies in exquisite detail. These observations will either confirm our standard cosmological model with new precision or reveal fundamental flaws requiring complete theoretical revolution. The convergence of data from multiple independent techniques means ambiguity should dissolve. We will know whether dark energy is constant or evolving, whether expansion is accelerating or decelerating. The implications extend far beyond academic cosmology into the ultimate fate of reality itself. If dark energy strengthens, the universe will expand forever, eventually tearing apart galaxies, then stars, then atoms themselves in a big rip. If it weakens sufficiently, expansion could reverse, collapsing everything into a big crunch. If it remains approximately constant, the cosmos will continue expanding and cooling for trillions of years toward heat death. Our civilization possesses the privilege of living during the brief window when the cosmic microwave background remains observable and the expansion rate measurable. In the far future, cosmic expansion will have carried distant galaxies beyond observation horizons, and the CMB will have redshifted to invisibility. Future civilizations might never discover the Big Bang or cosmic expansion, forever ignorant of their universe's history. We are cosmological pioneers exploring the universe, while evidence of its origins remains accessible. The duty falls to our generation to decode the cosmos, while its secrets can still be read in the sky. Every measurement of distant supernovae, every map of galaxy clustering, every analysis of CMB fluctuations brings us closer to understanding our place in the grand cosmic story. The choice before us is clear. Pursue these mysteries with the full force of human intellect and technological capability, or accept ignorance about the 95% of reality we cannot see. The universe is revealing its secrets at an accelerating pace, offering insights that previous generations could only imagine. Time is limited in another sense. As a species, we must solve the sustainability challenges threatening our survival before we can pursue cosmic understanding indefinitely. The same scientific method revealing dark energy and mapping the cosmic web must be applied to climate change, resource depletion, and existential risks. The ultimate weird fact is this: we exist in a universe that permits self-aware structures complex enough to comprehend their own origins and contemplate the cosmos's eventual fate. Conscious thought emerged from quantum fluctuations in the primordial universe, evolved through stellar nucleosynthesis and chemical complexity, and now turns its attention back toward the initial conditions from which everything arose. The universe is not just expanding, it's awakening to self-awareness through beings like us, who can measure, analyze, and ultimately understand the reality we inhabit. We are the cosmos becoming conscious of itself, using mathematics and observation to decode the deepest mysteries of existence. The journey through these 101 weird facts reveals that our universe is far stranger, more dynamic, and more mysterious than simple expansion models suggest. Dark energy evolves. Space itself may be alive with quantum fluctuations. The fundamental forces might be changing. Reality exceeds our current comprehension. But the human capacity for understanding has proven remarkably powerful. We've decoded cosmic background radiation released 380,000 years after creation. We've detected gravitational waves from black holes colliding billions of light years away. We've mapped the large-scale structure of the entire observable universe. We've measured cosmic expansion to within a few percent precision. If we can measure and map the invisible 95% of reality, decode the mathematics of curved spacetime, and peer back to the universe's first moments, then surely we can resolve the remaining mysteries about dark energy's nature and the cosmos' ultimate fate. The message from the universe is clear. Reality is comprehensible to sufficiently determined intelligence. The weird facts that perplex us today will be understood science tomorrow. The mysteries that seem impenetrable will yield to observation, mathematics, and human creativity. We are living through the golden age when fundamental cosmological questions will finally be answered. Within this decade, we will know whether dark energy is constant or changing. We will understand whether expansion accelerates forever or eventually reverses. We will discover our universe's ultimate fate. The cosmos is speaking. The data is arriving. The observations are accumulating. The mysteries are yielding. The choice is ours. Embrace the challenge of understanding reality in its full strangeness, or accept ignorance about the universe we inhabit. The weird facts assembled here are invitations to wonder, opportunities for discovery, and challenges to comprehend. Each represents another piece of the cosmic puzzle we are learning to solve. The universe is waiting. Deep time extends before and after us. The ultimate truths remain encoded in mathematics we are only beginning to read.